Okay, it's 12:30, so let's start. So thanks for being here. So it's my pleasure today to introduce Mattia Pistone, who is here as the distinguished lecturer for this year's for the ICDP program, and it's sponsored by GSA, right?
GSA.
And so just as a short introduction, so Mattia did a master in geodynamic, geophysics, and volcanology at the University of Rome. And then he did his PhD at UPH with Peter Ilmer, and he got his PhD in 2012. Then he did a first postdoc at University of Bristol with John Blundy, and then a second postdoc at the Smithsonian with Liz Cochrane.
Yeah.
And then a lecturer position at University of Lausanne in Switzerland. And in 2019, he's joined University of Georgia. And it has been announced officially, so in a few months, like July 1st, he will be an associate professor with tenure at the University of Georgia. Thank you.
Thank you very much. Thank you. Thank you for inviting me. First of all, Sarah, everyone, for having time also to talk to me this morning. And then I look forward also to the coming meetings this afternoon. Hopefully, I will not make you asleep with this lecture. So therefore, I hope that we will not go to hibernation, essentially, especially with such a great weather. And for me, it's a great pleasure also to present, first of all, this lecture. So just to remind everyone that you can ask questions while I talk. So I hope you are not going to be passive listeners and just to be silent and just listen all what I vomit. So I really wanted that if there are topics or statements that requires also some clarifications, please stop me anytime. That's also the nature of the lecture, to educate, but also to essentially be involved together in this educational experience. Despite the big title, Distinguished Lecturer, I'm not so distinguished also because I'm Italian. So anyhow, I take it, of course, but essentially, I'm just a normal man with a long list of defects. So I try to do my best today to essentially introduce you to a project. I'm one of the leading PIs. We are 7 in total. Again, giving all the leadership to Italian people is dangerous. So that's why there are the 6 people backing up. And essentially is a project that is within a framework of a long historical effort. This mission about reaching to explore to sample directly in situ the crust mantle transition is not a new idea. So we are actually the end project towards the same effort. Therefore, there is a long historical shot that comes actually from the end of the 50s, early 60s, that will be part of the first part of the talk. So I will give you a little bit a historical tour to start with, before to give you the contextual information. Then I will move to the DIE project. Then I will also spend, hopefully, the last 10 minutes of the talk to mainly address what I'm specifically doing from my side. The project is very large, or large breadth. So there are many topics that unfortunately I will not be able to cover completely. For instance, the microbiological efforts, so people that are studying a potential deep biosphere in the Earth's interior. I will make a few mentions, but unfortunately, because of my background, which is not specialized in microbiology, and don't take the risk to walk in a minefield to say BS potentially. So therefore, I will do essentially a tour that will be mainly based on what I know best. So I'm being educated, especially in petrology and geochemistry, and also links with volcanology. But we will not be very close to volcanoes today. So we are going to be exploring the lower crust and upper mantle and the interface in between, so the Moho. Just a few words. So I'm here also thanks to a GSA, the Continental Scientific Drilling Program of the Geological Society of America, who is sponsoring mainly my travel. So I'm being able to go. I studied last semester on institutions mainly on the eastern part and Midwest portion of the US. This semester, also due to the coming spring and summer, I'm coming to the West. So, and you are one of these important sites to present under the flagship of GSA. This is a program that funds mainly students. Is a program of GSA that provides funds for both undergraduate and graduate students to study rock cores from any drilling project. So that does not need to involve only deep Earth's interior, but also project on, for instance, paleoclimatic studies with lake sediments, or rock cores are being collected also for geothermal energy exploration. So there is a very large array of opportunities, and the GSA program offers travel grants that generally covers the travel and the lodging, and they allow to use for free facilities mainly located at the University of Minnesota, where the CSD division is located, with Anders Noren as the actual director of this program within GSA. And then if you want to know more information about that, you are lucky to have Marie Jackson in your department, because she has been one of the main drivers, as she reminded me this morning, she has been one of the main drivers during the pandemic, which sucked, okay, as you know, to essentially drive and manage this program. So therefore, she's your internal contact that if I were you, I will go to bother her with a lot of questions. So thank you, Marie. Sorry for volunteering. So let's speak about the Moho. What is the Moho? So the Moho comes from the name of this seismologist from Croatia, Mohorovičić, which is a bit a difficult name also for me to pronounce. That's why conventionally we use the short form that can be easily pronounced worldwide, which is Moho. And these seismologists, they in 1909 published the first evidences of a sudden jump of primary wave velocities, or P wave velocities, going from less than 7 kilometers per second to more than 8 kilometers per second. And that jump was interpreted as the transition from the crust to the mantle. And over here you see the onion structure of our planet. Of course, as you can see, it's a pretty busy, artistic view, of course, simplified. But what I like about this visual is that on our planet, because we have active plate tectonics, we don't have a sort of boundary that is uniform everywhere. So if you take the moon, based on the most recent accepted hypothesis of the internal structure of the moon, looks like the moon is pretty boring, because you have an anorthositic crust with a relatively equal thickness everywhere, maybe slightly modified by impacts, but overall the crust is identical everywhere. Also with the lack of evidences of active plate tectonics of that planetary system. Instead, on planet Earth, we have a much more diversity. Sorry. Speaking about tectonic diversity, sorry. So greater ranges of complexities, where you have oceanic crust, continental crust, different thicknesses, and therefore also for geophysicists, who are going to be a big part of this talk. Again, I'm not a geophysicist, but it's a great part to do the internal radiography of our planet and to understand what is below our feet. And drilling is the one that should allow us to understand what is the column or the stratigraphic sequence of rocks, mainly in this case capture, using an oceanic column, oceanic lithospheric column, capturing crustal and upper mantle rocks, and mainly magmatic rocks, but of course you can find also metamorphic rocks, and real on the top of this sequence you have oceanic sediments, so therefore also sedimentary rocks. But today I will focus mainly on magmatic and metamorphic rocks. And in this column, as you can see, over here you have a sort of a simplified translation of what would be the radiographic signal from a geophysical standpoint. We can have a sharp boundary at some point, but here is the problem. As a petrologist, we experience a big headache, migraine, essentially, to understand what that boundary is located. That could be very well visible by geophysical signal, but then it's difficult to translate into a rock type. Now here I vomited all the very peaky description of the rocks. Let's do a much more brutal translation. This is a sort of boundary. that I should expect, going from crustal rocks that are dominated by felsic minerals like plagioclase, so like mafic rocks or gabbroic rocks. Here you have also some dark, looks like a zebra rock with dark paroxenitic bands that are generated also a folded banding into a gabbro that was deforming during emplacement. And over here there are some students from the University of Lausanne that I brought in the field in 2018 to show some pieces of mountain rocks, lerzolite, with also beautiful ultramafic veins. They've been studied again by Marie for the first time with some French researchers. But if I do another brutal translation, is this one of the hypotheses? It's not a unique one. One of the hypotheses is that the jump from crustal to upper mountain rocks should go from rocks that are mainly made by a lower modal proportion of mafic minerals. Mafic means minerals enriched in iron and magnesium, like olivine in this case, or pyroxenes. And then the crustal domain should have a much more felsic minerals, plagioclase, also very popular, like anorthite, in high temperature gabbros. And with a modal proportion of mafic minerals that is lower than 90 volume percent. Above that percentage, you deal with ultramafic rocks expected for the upper mantle. But as you can see, now if I want to find my petrological Moho, I have a problem to do the correlation. And that's why there is this need to essentially calibrate geophysical signal, a petrological language, in a way that we can determine what is the origin of that big jump in seismic wave velocities from crust to mantle domain. Let's go to a sort of Mickey Mouse cartoon, but is essentially a simplified version we show in many introductory geology lectures. So especially students that for the first time, they are going to face a geological topic. So you go simple. You don't show the full sequence of description, otherwise the class will get empty. Everyone will run away from geology. So, but these are essentially also with this simplification, you can see the tends to plate tectonics. Also here we have two categories of domains. A domain where the oceanic lithosphere is thinner, especially because the crust is thinner and the upper mantle is located closer to the surface or to the bottom of the ocean, precisely. And then the continental crust, especially if you approach orogenic bodies, so where you have mountains, you can have a pretty large thickness. Now, a question I have for you is, where will you go to drill? What will be the first target to drill that is also relatively easy, also from an economic standpoint? So you drill, you reach a deep target, but without spending too much money to drill 1,000 kilometers over rocks, essentially. Oceanic crust, that would be the easiest target. Now, bear in mind, because we are geologists, we also deal with rocks that, due to tectonic processes, have been exhumed. Therefore, you have what is called ophiolitic structures, so essentially fossil oceanic crust or oceanic lithospheric blocks that have been brought to the surface. And we know that by looking at these pieces of fossil of oceanic domain, we don't have always this beautiful or expected ideal scenario where you have a jump or a brutal, sharp transition from crustal domain to upper mantle domain. Most of the time is something much more complicated, much more diffuse, gradual. But that's why drilling is powerful, because we can capture this gradual transition, especially if we drill in areas where we have a continuation of the transition from crust to mantle. So if there is no faulting, we have a continuous stratigraphic log, maybe we can understand how this Moho looks like from a mineralogical and lithological standpoint. Now here, this is a real Mickey Mouse cartoon I did to show essentially how deep we went with drilling in oceanic environment. And before doing that, here is, I remind you, the historical moment when drilling inside the Earth's interior became important. Everything happens a little bit after the Second World War. In the 50s and 60s, we start to have the Cold War. In other words, the geopolitical competition between Soviet Union and the United States of America. What happened is at that time, there were three important races. Number one, which nation was bringing the first man in the deepest bottom of the ocean? Over here, there is the bathyscaphe Trieste, made by Italians, designed by Swiss people, which is very outstanding. Switzerland has no ocean, by the way, but they know engineering, okay? Constantly by also German people do tough materials, so they help the Italians, and was purchased by the Office of Naval Research in 1959. In 1960, they brought the first two people, Jacques Piccard, a Swiss engineer, who designed the bathyscaphe, and Robert Dietz, the first oceanographer in the history, going to the Challenger Deep. So first race won by the US, American flag on the bottom of the ocean, right? The second race that I'm not going to talk about, actually you should teach me about, is the race to the moon. And you know already that history, and you know who won that race. Now there is a third race, which is about who is going to reach the Moho. And that was part of the same historical race or competition, which actually, by the way, while there was a geopolitical competition, there were a lot of money for research. Indeed, the first project attempting to cross or to explore the Moho was the Moho project funded by the National Science Foundation. And that project started with $7 million, okay? Now, $7 million in the 60s are equivalent to $70 million today. So $1 is equal to $10 today. So remember this inflation that happened. So the project, when they started to design and then they actually went, exploded to $70 million at the time, which became $0.7 billion today. To drill, and then this is explained in that book that was published in 1961 by William Bascom, and the target was to drill throughout the entire oceanic lithosphere, and then to reach essentially the upper mantle rocks. How much did they drill, according to you? For $0.7 billion in current currency, for the first project ever, offshore drilling. You don't have to tell me the depth, but tell me the lithology they reached. The answer is easy. They didn't reach them all. That's the short answer, okay? But what lithology did they reach? The gabbro? You're pretty positive. So they reach only the sediments. So the yellow part, the deep sediments, beautiful sediments, by the way. But essentially what happened is that mission, of course, in terms of target, they failed. But imagine that in 1960, when they did, 1961, when they decided to do drilling, they did an amazing experience. Like they took an old vessel from the Second World War, and they took the best drilling tower from Texas, put on the top of the vessel. Now, we are used to fantascientific movies. We are hyper-simulated with a lot of fictional stories. But this, 1961, with zero technology we have nowadays, they had this crazy idea. That was outstanding. But anyhow, without even reaching the target, they demonstrated they could drill offshore. And that was just a spark of an amazing historical sequence of successful missions. And I want to remind you the Glomar Challenger. Thanks to the drilling of the Glomar Challenger, we generated a foundations of plate tectonic theory. Thanks to drilling. They drilled rocks from the mid-ocean ridge system, like in the Atlantic, going further away. They realized the rocks were becoming older by getting away from a mid-ocean ridge system. They realized, there is expansion of the ocean. South America and Africa, as Wegener hypothesized already in 1915, and nobody believed in him, he was right. That essentially there is a movement, drift of the continents, so plate tectonics. Then we had a JOIDIS vessel, which actually recently retired in September 2024. Now we have a problem that ICDP is frozen right now, but actually is archived because there is no vessel. The US has no capability to do drilling right now, at least offshore. GQ is still available, but Japan has not enough funds to even maintain the vessel. So they do very few missions. The last one was for the Tohoku earthquake fault zone, the one that triggered the Fukushima earthquake in 2011. They did last year. But GQ is not operating always. As you can see, by taking all the data from ICDP website, they never reach, they never drill the complete sequence. They drilled mountain rocks. They found mountain rocks, but most of the time were already exposed and altered on the bottom of the ocean. And when you go already in the upper domain, you don't know where is the boundary of the Moho. So to know the boundary, you need to know, like when you do field mapping. If you want to know the border between two units, you need to know rock 1, rock 2, and then you place the boundary in between. But if you collect only rock 2, you'll never know where is the boundary with rock 1. So the same means for the Moho. And now the unique nation can do potentially can put the flag on the Moho is China. And this has been released this year in January. Mengjiang, if I pronounce with my great Italian accent, Chinese language. So this is the Ferrari of China that can drill up to 7 kilometers from the bottom of the ocean. So beside the kilometers of water of the ocean, they can go up to 7 kilometers. But now it's on the paper. We'll see when it goes in action if really that vessel can operate so deep. But at the moment, it's a unique nation. They have an operating vessel like that to do deep drilling in the ocean. Now, let's go to the continents. Now, of course, before you suggested, let's go to the ocean because the crust is thinner. But if you go to the continents, it's a sadomaso experience because the crust is much thicker. The target is further away. But the advantage is you are not in the ends of the ocean, especially the ocean can be rough. So therefore, drilling the open ocean can be challenging. On land, you have much more firm. The problem is, and now here I report also a very simplified view, how the Moho looks like in continents. Good luck. It's even much more difficult to find a sharp boundary or a reflector or anyhow transition from crust to mantle because the continental crust is thicker. There's also this build-up in a longer geological timescale. In a longer geological timescale, you can superimpose so many geological processes. So in other words, you can modify also that boundary multiple times and shift also the position of the boundary, depending on the processes that are contributing to make growth or thin the crust, depending on the conditions. If you are generating mountains, you thicken the crust. If you have a rifting, you are thinning the crust. So also shifting the position of the Moho and geochemically changing it will not make you like, you don't find the Moho with the label, hey, I'm here, you know, between the rocks. So it will be even much more diffuse to find it. And then I want also to remind you the models, how much do we know about the Moho? These are the most recent models being proposed. And this model has been proposed also with a careful thinking about what are the possible geochemical recipes to make the continental crust for equivalent geophysical signal. In this case, observe also from a thermal property perspective, the mantle flow and the thermal outflow from the solid earth. As you can see, for equivalent values, they do not change really dramatically. You have a very different structures. And these are what I call the box models. But the box model forgets one thing, the vertical variability. That is very important because in a model, that is the average composition, but you don't have homogeneous rocks. Rocks can be very variable within this single box. And now if we consider the variability, these are essentially the models being proposed in the last 30 years, at least. Silly and dikey, silly and mushy, blobby and dikey crust. Of course, this is a very simplified division, okay? There are also a lot of gray zones between this and this and this model, okay? So I'm trying to simplify, but simplification doesn't mean it's like that only and that's it. Geology is much more complex. And but as you can see, especially when you have verticalized structures, especially geophysicists, I believe they are in the room, they will tell you that to image verticalized structures is almost impossible, or they become very difficult. They look like invisible. Because generally it's much easier to see horizontal or sub-horizontal features when you do, for instance, seismic tomography, rather than something is verticalized. In fact, for volcanologists, it's very difficult to know the conduits, they are verticalized structures. Instead, if you have something, a reservoir, like Yellowstone, it's easy, it's fucking big, right? But if you go to Mount Etna, Italian volcanoes are little ants, right? You don't see magma chambers. So the short information is here that also here from a chemical composition, compared to the box models, also here is very different. What would be the composition of the crust? What you learn from geology 1000 level, it is we use 1000 level in University of Georgia. I don't know what type of level you use here for introductory courses. We say that the back composition is andesite, like the same composition you see in the Andes, where andesite name comes from. But it's not like that. I will try to give you a demonstration in the coming slides. So, to sum up, we have proved that the crust mountain transition is very diffuse, very largely, due to the longer age or time scale of growth, formation, and evolution of the continental crust. We have geophysical data that can be also much more difficult to decipher. We have very few outcrops, especially rocks that are coming from deep regions that are exposed to the surface. And then, most of the time, when we go to active volcanoes, the volcanoes sometimes they vomit rocks that comes from deeper regions in the lower crust upper mantle, we have a sense of xenoids that can be used to understand what type of composition you have down there. But it's like having a piece of a puzzle, or few pieces of a puzzle, and try to construct the entire picture from a spatial and time standpoint of the lower upper crust. And there are geologists that do that. They are very brave. I respect them, but still, it's still a mission impossible to reconstruct a very large chunk of the lithosphere from a few pieces of rock vomited by volcanoes. So that is a problem. Speaking about puzzle, drilling is serving exactly to capture a sort of column, continuous sequence of puzzles. If you have a sequence of puzzles, it's a bit easier by inference to understand what will be the picture. Compared to xenoids, I told you they can be randomly taken in different positions, but you don't know how they are arranged between each other. And then drilling can help you to understand one of the targets, the Moho, the boundary between crust and mantle. How do we divide that? So let's go to this new Mickey Mouse cartoon of mine. By the way, I made a great effort. I hope you are grateful with me because I put in miles. I'm European. I've been trying to use the miles, okay? And I'm also cheating in this plot. You see the first mile is exaggerated by 3.5 times for visual purposes, okay? Then any other mile is identical. So I was not drunk when I did that, okay? So, now, what is the deepest natural borehole? Actually, it's in France. It is a cave in the French Alps, not far from Grenoble, from the Italian border. But now, any other borehole I'm going to present are either for mining operation. I believe you are familiar with something in your state. What is the greatest mine you have in your state? Or Bingham Canyon? Is the same or is a different one? Probably I'm ignorant and now I'm learning a new mine I was not aware of. So this is the deepest one in the world so far in South Africa for gold extraction. Then we had, let's return to the competition between Soviet Union and US. In the 70s, the US made the deepest borehole that was meant also for natural gas and oil extraction in Oklahoma. It was 6 miles deep. They realized that most of the oil and natural gas reservoir are at shallower level. Therefore, that was the first and last borehole so deep for fossil fuel extraction made in the US. Then the deepest borehole ever made was made by the Soviet Union in Kola Peninsula, very close to the border with Finland and Norway. Now it's a pretty hot border with the new geopolitical conditions. But here you have the rusty cork in meters, 12,226 meters, which is equivalent to 7.6 miles. They also did a more recent borehole, now the Russians, not the Soviets, but they are the same, that essentially they went to around 7.6, 7.7. So why we are not able to drill deeper? What is the parameter they think apart from temperature, but most of the drilling operations are made in cold environments, where the geotherm is low. When you go deep, it's not too hot. The metals will not expand, will not get stuck, and so on. So what is the other parameter that sucks when you drill deep inside the Earth's interior? Pressure. The deeper you go, the higher the pressure. So before we mentioned Bingham Canyon Mine. So that's the deepest borehole in Utah in comparison. It is this based on information I found on a report published in 2017. I don't know if there's been further digging, therefore that value could be further increased. I don't know that. But anyhow, you can correct me. You are expert from Utah. So over here, you can see that drilling arriving to this target is essentially impossible with the present day technology. Now, the question I have for you is, what is the option? In the ocean, so far, we are not reaching there yet. In the continents, looks like, especially if you consider the average depth of 35, 40 kilometers, slash 22 miles deep, is beyond our reach. So is there a way that we can circumvent the probe by maybe targeting some specific tectonic settings? Extension. That would be an amazing part. By extension, will also bring you the rocks closer to a surface, but you have a lot of stretching too, so a lot of faulting too, right? But if you really want to get deep rocks, what is the other process? Besides rifting, rifting can also bring rocks shallower, but then you don't generate necessarily already at the beginning very deep rocks. The pressure is already low during rifting or extension. So where do you encounter rocks that were generated very high pressure, even down here or below, in the upper mantle, but then still come close to the surface? Where do you go? Areas where you have a sort of toothpaste effect. You extract the toothpaste out. So essentially, what I'm indicating in this case, what is the regime, tectonic regime I'm referring to? Compression. So here, of course, is a simplification. So exhumation during compressive tectonic settings. However, this is a simplified cartoon, but I should report a lot of faulting. That is one of the most common cases. You crack the original vertical ice column, and maybe you can remove a lithology, so you can displace them. So in other words, most of the time, exhumation, for instance, during formation on the mountains, you are going to jeopardize the original sequence of rocks from the crust and upper mantle domain. But there is one area where this has not happened at a very large level, which is Italy, the Ivrea-Verbano zone. We are not far away from Milan, so we are in the western side of the European Alps, and all the colors indicate different units. To simplify, these are the upper crust, this is the lower crust, and this crust, as I told you, is a continental crust. However, was generated by two chapters. So if I refer to like a book, is one of the books of my son who is 2 years old, very easy to read. 2 chapters, so not complicated story. There are 2 sequences. One is a meta-sedimentary sequence of essentially going from gneiss in the green schist to amphibolite facies, then to metaphylites to amphibolite and granulite facies produced in the Paleozoic, and then in the lower Permian, 185 million years ago, you had the intrusion of magmas, giving the second chapter, the magmatic history of the crust. So therefore you have a lot of gabbros in the lower crust reported in green, and then granitic bodies like magma chambers fueling a caldera-forming system that generated Ygritte-Brights reported in pink color. Now, this is the history reported here. So the crust of the Paleozoic crust comes from the Variscan origin, which by comparison was coeval to the Appalachians in the US, more or less. The Appalachians survived. The Variscan was completely eroded. There are very few chunks in the Pyrenees, in the Alps, but nothing is left of those ancient mountains. So What happens is that for this generated a big sequence of sediments that got metamorphosed, they became schist in the upper crust, and then gneiss plus metapelite sequences in the lower crust. And then where there's been a little bit of rifting, they allowed some magma to come and then to intrude and generate a very evolved transcrustal system from the lower crust to the upper crust with a volcano on the top, sort of mini Yellowstone of Italy, of course, much smaller size, that essentially indicated a transformation of the crust from a geochemical standpoint. We went from felsic rocks to something very mafic in the lower crust and very felsic on the top. So the magmatism generated sort of separation, geochemical separation from lower and upper crust. Now, if I take that map and show you, sorry for the lower resolution, and I rotate it, today I have a tilted, horizontally tilted crustal section growing from the bottom to the top, including volcanics. And now if I do an ideal section, I want to demonstrate you why this crustal sequence is continuous and preserved. I told you it's been exhumed during the formation of the Alps 30 million years ago, but the crust was produced in around the Paleozoic and last time mostly 280 million years ago, with something occurring also in the Middle Jurassic 180 million years ago, but not so much. So now this preserved crust has been pushed out like a toothpaste out of a tube, and what we see as a geophysicist, if I take rocks and then I do some laboratory simulations in the lab to propagate seismic waves, I can see that there is a general linear increase of most of the rocks, with some exceptions, maybe because of different lithology, different isotropic character of the rocks have been measured. But overall, you have an increase in velocity. And then what I like, approaching velocity, I told you, the one spotted by Moho, the seismologist from Croatia. Then as a petrologist, I want to see, for instance, how dense the rocks are. Actually, these are also a piece of information very important for geophysicists. The higher the velocity, the higher the density. Looks like there is a match between the colorful symbols. And then over here, all the minerals have been interrogated by petrologists to know at what pressure did you form, dear mineral? And then as you can see, there is a linear increase. The deeper you go, the larger is the pressure. So what does indicate that now I don't see the faulting that is jeopardizing my sequence. It looks like it's preserved, especially in the lower crust approaching the potential upper mantle. Then back to geophysics, below the Ivrea, again, this is the entire Ivrea Verbano zone body, without now discriminating all the lithologies, just in yellow. This is the largest geophysical anomaly of the entire Europe. So there is a very dense body close to the surface. The body is much, much denser than any other rock that is around. Here, with another Mickey Mouse cartoon, so that is the original main last snapshot of the two-chapter continental crust of the Ivrea. During the formation of the Alps has been uplifted and tilted. And there is this geophysical body, the Ivrea geophysical body, which has high velocity, high values of gravity, so in this case density, based on gravimetric measurements, high magnetic properties not reported here, but there is something very dense close to the surface, something that should be deeper, but it's close to the surface. And in terms of velocity, dp, primary waves, the Ivrea has average velocities that are larger than any other tectonic setting worldwide. Indicated there is a deep, dense body, high-speed body close to the surface. Now, and then I want to complete with this last slide based on rocks. This is an exposed continental crust, so let's trust what we see, what we observe. These are rocks, especially going through the mafic complex, so the last big blob of magma, of course, constructed by different pulses, okay, throughout geology, a time scale in 5 million years. And then I go to see the rocks. What did I tell you about one of the hypotheses to go from crust to upper mantle? Is to look at the modal proportion of the minerals, mafic minerals versus felsic minerals. Felsic minerals in terms of plagioclase. commonly found in gabbros. You see, you don't need to be a rock scientist, sorry, to see that the plagioclase is decreasing while I go deeper and deeper in that sequence of the exposed continental crust in the magmatic portion. And then as you can see, sorry, I could not fit all of them. The sequence continues here until these rocks are paroxenated. Then the mantle rocks, chunks of mantle rocks, they've been encapsulated before the arrival of the magmas. So these are enclaves of mantle that are also here. Now, these mantles, they've been encapsulated in lower crust, potential for some tectonic setting like the Variscan orogen, with some subduction zone environment, therefore there are chunks of mantle being disrupted. But again, if you find a piece of mantle here, does not indicate this mantle has been taken from 40 kilometers and then brought up like a rocket for 40 kilometers shallower level. So in other words, if you find the mantle, you can smell the mantle, the real bigger body down there. By crossing, making cross all the data I show you so far, from a geophysical, petrological, mineralogical, and laboratory standpoint. So if I am a truffle dog, I see this, I can tell you, yeah, the truffle is very close potentially. Okay? So this is the exciting part, the motivation of dive is the most complete continental crust that have been studied so far. And potentially we can drill, if that body is a piece of mantle close to the surface, we can drill without going deep. And that is the best case for generating dive project. We are not in oceanic environment, so we are not really diving the ocean, but the idea is to dive to explore that environment. And the idea came from my former advisor, Luigi Burlini, was one of the advisors during my PhD. Unfortunately, he died due to leukemia during my PhD. For him, it remained a dream. And me and the other guys are carrying his legacy. So therefore, we are not doing any special, trying to honor Luigi and bringing forward his idea to drill in this area, because this is an area where we can reach the transition between the crust and the mantle. In 2017, we did a workshop to generate a manifesto. So what we want to drill, for what we want to drill. Again, I'm going to focus on the petrological, lithological part, but the idea is to respond to this correlation between geophysics and petrology, to understand the deep biosphere, try to understand the architecture of the crust, and what it means to go from the crust to the mantle, how this is, they are interacting between these two spheric domains in the onion structure of our planet. So these are the boreholes we did in the phase one. This is the one that will be in the future. It is also the most ambitious one because we want to drill for 4 kilometers. And there is a geometric progression of cost. Every kilometer is twice the price of the kilometer before. Therefore, going for 4 kilometers is not cheap. If we want to recover 4 kilometers of rocks, it's at $15 million with the current rate. Let's see when the inflation will do. Maybe it will be higher. Over here, we spend $4 million for 2 boreholes. They all together, they do 1 mile deep drilling or 1.5 kilometers. So let's go what we need. So drilling is something that requires a lot of planning. Of course, here I will go a quick fly, very quick, but this requires years. Okay? This requires even before the workshop in 2017. Since Luigi died in 2009, we've been thinking about that. And we started to drill only in October 2022. So you do a calculation, it took years. So drilling, for instance, in the 2 drilling are one for the Paleozoic crust characterization, and the other one for the magmatic crustal characterization. So essentially to capture the 2 chapters of the geological history of this crustal section. And what you can see is that we've been drilling in an antiform. Why? Because the antiform is a structural, there is a structural geology exam, I'm being told today, maybe it's part of the exam. So there is the antiform, you have the older rocks, deeper rocks in the hinge zone. So if you drill exactly in the hinge, you even drill less deep because you take advantage of this morphological structural shape. Of course, drilling a hinge zone comes with some risk. This is what we try to interpret from geophysical sequence, shallow geophysics, try to interpret how the structure look like. But then when you actually drill, you realize that what you plan at the beginning could actually cost you or be advantageous. In our case, we were in the in zone, but was a little bit more tilted than what we expected. We started to go in the lean zone. In fact, we stopped earlier. We wanted to do 1 kilometer. We stopped at about 578 meters. You know, if you drill in the lean zone, you drill the same lithology forever. You don't learn anything, okay? So, but the rocks are amazing. These I call the geoporn. Why? Because there is a cluster of processes. This was originally sedimentary rock. Now, in terms of sedimentary rock, what survived was the layering. Only that. In terms of original sedimentary rock, was a clastic rock, was essentially a rock that now, or that protolith, only a little bit is a textural observation of layering may have survived by its complete metamorphosis in the granulite phases. So above 550 Celsius, actually this rock probably locally has been heated up by the intruding gabbros in the Permian. And now you have these pinkish layers that sometimes they also circumvent bigger minerals, especially of quartz, albite. These are K-feldspar. It's a partial melted rock. Then the regional name is stronalite from the Valstrona, Strona Valley, but essentially is essentially a partially melted granulite rock of metasedimentary origin. And this is the rock that I used for my TED talk a couple of years ago. As you can see, the defoliation is one of the rocks from the limb zone. Defoliation tells you whether you are going correct or not compared to the drilling. We wanted to drill perpendicular to the defoliation. When we start to go to the limb, the defoliation starts to be subvertical. And this is when we realize, oh crap, we are on the limb side. And these are what made excited all the microbiologists to find these pores. Now, this one in particular was not the best because it was too big. It was contaminated by the water used for cooling down the drilling apparatus. But there are so many other pores that are at the micro, even nano scale, that the microbiologists are targeting to understand if there is a microbial matter. Extremophiles, if Will agrees with the term I use, I'm not a microbiologist, but since biotas that can live under extreme conditions, in this case in absence of light. Then we did a second borehole, inclined, as you can see, because we want to drill perpendicular to the reflectors being observed and interpreted, identified geophysically. And also here, when we started to drill, we did what you do with the classes of Serra or Juan Carlos in the petrology classes. What do? Especially for a magmatic rock, you determine the modal proportion of the minerals, you classify what type of rock you are looking at. That is Geology 1. And this is what most of the students did in the field. I've been doing competition with the students. A couple of students were even they bet me. It's not something very proud to say, okay? I'm supposed to know more than students, but I was very proud of the students that did a very diligent job. Try to describe, as you can see, following the sort of template we provided for rock description, when the rocks were collected every single time. Here you can see a rock that is being cut. The sound, fortunately, is off because it's very annoying sound when you hear the blade cutting the rock. And the rocks were cut because sometimes we got a 3-meter long rock core, but they need to feed in the box. That's why they were cutting. And we were cutting the rocks. At the beginning, we were so excited, filling up every slot, but we forgot that some rocks are 3.2 grams over cubic centimeter. And these are PQ diameter, 85 millimeter diameter rock. So by the end of the day, I was becoming a hobbit because it got shorter due to the heavy weight. These were 250 pounds heavy boxes. So we need to leave one slot, a central one, empty to be able to lift them, or to call Schwarzenegger probably. So over here is a synthesis of the two boreholes. The one that excites me out most is this one, the magmatic one. In line with the rocks on the surface, I show you where the modal proportion of the light color minerals like plagioclase decreases. Is something we observe also in this borehole it looks like the rocks becomes much, much more mafic, or in cases, ultramafic. And this is the synthesis for the first borehole. And then that's the second one, where also we observe a lot of garnet. Sometimes the garnet at deeper condition became as big as my fist. And it also indicates larger density. So therefore, you don't have only a different proportion of minerals, but also a proportion of minerals that are denser while going deeper. So there are therefore physical and geochemical processes that are acting all together, and we are still trying to identify what they are about. But now I'm going to focus, and that's the very little last chapter of the talk of today, on what I'm working on my own with other scientists. We are about 20 scientists that we got excited with the pseudotachylite. Now, pseudotachylite is a rock. So if I translate this very old and counterintuitive term, the pseudotachylite means it looks like a tachylite formed by a meteorite. So which means that it is a sort of glassy material produced by the impact of a meteorite body on the surface of the planet. But pseudotachylite is essentially a rock produced by earthquake. It is actually probably is one of the most exciting common ground we have with geophysicists. The geophysicists tell us about, or rock physicists in general, tell us about the dynamics of how to produce a pseudotachylite. We as petrologists try to determine how the pseudotachylite was formed from a geochemical and petrological standpoint. And that was the mission. Now the question I have for you is, if you are familiar with the pseudotachylite, how do you produce them? What is a mechanism in general that you require to generate a pseudotachylite? These are two sides of a rock. They are sliding against each other, okay? So what is going on in between when they are sliding against each other along a crack? Friction, right? What does friction? If I do on my hands, I have very cold hands because, of course, I'm a bit nervous, adrenalinic while presenting. So if I do that, what do you feel? Heat. So increase of temperature. So this has been the conventional, a very plausible explanation to explain the origin of pseudotachylite. You need the friction, and if the friction generates enough heat to overcome the solidus temperature of the rock, you induce a partial melting. And therefore you generate something molten that then freezes quickly, because generating earthquake is, geologically speaking, is an instant or something that occurs in a very short time scale. You melt, but you freeze the system. And that's why pseudotachylite, if it's fresh, if it's not altered, is glassy. Okay? But now what I challenge you is probably, that is what I've been testing on rocks from Balmucha, not yet on the rock cores, but the rock cores are the next target for this investigation, is that friction alone is not enough. You need something else. So let's go to petrology plus 0.1 about how to do partial melting. It is the so-called dry or water-free solidus of a mountain rock, a lerzolite. This is the temperature at which Balmucha peridotite was located in the Carboniferous just before the lower Permian magmatism, when this pseudotachylite had been dating or proposed were formed around 320 million years ago. And that was the original temperature and pressure condition. So the Balmucha peridotite was pretty cold. So it was solid. It was not a partially molten mantle. It was solid mantle. And now you generate a pseudotachylite. What is a conventional interpretation? You go straight, you do friction, you increase the temperature, you overcome the solidus, partial melting, you freeze very quickly back to the original conditions, and you generate a pseudotachylite. No issue, very clear. There is another process that is important, is decompression. Especially for petrologists teaching how to do partial melting of the mantle, one of the processes is decompression melting, as you observe in the mid-ocean ridge systems, for instance. Now, in this specific case, if I go decompression, the rock doesn't care, remains solid, right? But now, and then of course, even if I do friction plus decompression, that could be plausible, but again, it does not really change the first interpretation, right? Because again, it's easy to explain like that rather than introduce an additional process in the game. Just to clarify, why do I introduce decompression? When you crack a rock, you generate a gap at the beginning. That's a momentary or a temporary moment where you generate a low pressure environment. Decompression could be likely. But then now the question is, decompression is really favoring pseudotachylite formation, yes or no? Now, if you take, these are a lot of lines based on experiments. If you add water, the shape of your solutes completely changes. So now friction melting can still work, but decompression could be much more helpful. Why? Because the pseudotachylite you produce at the beginning, unfortunately, does not coincide with the chemistry that is forecast by using only frictional melting. And I give you a demonstration with this. This is a pseudotachylite from a Balmuccia peridotite, so this is a lerzolite hosting a very thin pseudotachylite. I'm using a thin pseudotachylite because I want to generate a model. When you generate a model, you need to demonstrate, especially one important thing, mass conservation, energy conservation, and then to discriminate what has been melted, what has not been melted in the pseudotachylite. Generally, in friction melting interpretation, everything melts, but it's not true. Indeed, when we do careful analysis, there are only a few minerals that actually melt, and the others do not melt. So this means there are PT conditions specific to melt certain minerals and not others. Now, for now, these are the factors I want to satisfy, so I need to conserve the mass. I need to identify what has been melted, composition in that glassy material, and then has to cool down fast, so the pseudotachylite should not recrystallize. Otherwise, any petrology modeling is jeopardized. I cannot model. So, here I introduce very quickly the type of modeling. You need the friction, for sure. A little bit of heat you need, otherwise no melting. But I need to demonstrate that thermal diffusion is very efficient. In fact, in less than 2 seconds, I propagate the heat entirely in the entire, in this case in 2D, in the entire thickness of the pseudotachylite. Chemical diffusion has to be slow and lazy. I want to identify the phase without getting becoming hybrid or melting together in one single melting pot. I need to recognize, oh, only olivine crystallizes in this portion of the pseudotachylite. Oh, yeah, only pyroxene, and so forth. And then water diffusion is important to lower the solidus that I need to make the process easier for melting, and then to cooling very fast in a way that the material remains glassy. It does not crystallize. So this is where pseudotachylite can be actually produced under near equilibrium conditions. If so, I target those with a larger, detailed, petrologically peaky approach, going with optical microscopy. Here you can see some floating clinopyroxenes, olivine untouched on both sides. Some spinel recrystallized only on the border. Probably this was a band recrystallized, but this is a very glassy material. I targeted that with a nanoscale analysis with a STEM, which is a TM with the same capability of SEM. And then I noticed these droplets in the glass. This spinel, and this OPX, but in a glassy form. These are the 2 unique minerals that melted. In a lerzolite made of OPX, CPX, olivine, a spinel has accessory mineral, so it means that it's not volumetrically important. But if I take now these targets, I say, there is only OPX spinel forming, while CPX in this case is floating, is not melted. What I can see is if I do modeling, that is my solidus temperature in presence of that amount of water. And now if I do friction melting, only friction melting, I don't make the composition I found in the real pseudotachylite. If I want to go there, what I need is the compression. So friction melting alone does not justify the composition of pseudotachylite identified in these mountain rocks from the Ivrea. So this is what we want now to test for the rest of the pseudotachylite found in the rock course. And also, decompression is a very important phenomenon because the idea is probably also the sequence of composition we see, because the rocks that we produce are not static. They come also from tectonic forces. And when they are produced, maybe also this game of PT condition varying also at the scale of a mineral or a single rock can be important to understand the transition from the crust to the mountain. I complete here with this slide. So essentially, there is a lot of going on. Of course, I don't have now I cannot tell you we found them all, but we are very close. Especially the second Boro is promising, but we don't have conclusions yet because we got the rocks for laboratory analysis last September. We are going to do this job for a couple of years at least. We need to characterize 1.5 kilometer long sequence. To do that, to be certain, and maybe we approach the Moho or not. Thank you very much for your attention. Yeah.
Hi, Doc. My question goes on the fact that it would be an anomalous place. How representative do you think that would be of a true mantle or pristine mantle? Like every place that the mantle is close to the surface is anomalous in some way, right?
The answer is very easy because it goes in line with what I said earlier. With active plate tectonics, you have a very large variability of lithological arrangement, and therefore also, in this case, also a type of mantle or a Moho architecture. So therefore, I would say Ivrea Verbaum zone will be the one on his own, but could not be the calibrate for the entire planet. So in other words, it's a bit different from the approach that, for instance, planetary scientists do with very few chunks of rocks, like lunar samples. They provide you the model for the entire moon. But that I understand because the moon is not very easily accessible. Here we have more access by the same time by drilling. If we manage with the Ivrea, we are going to have for sure a Ivrea calibrated mantle, a Moho architecture. We can extrapolate for other environments, maybe with a similar geological history, but absolutely cannot be applied worldwide. No way. Would be an arrogant statement for sure. But still better than nothing we have so far. So that's a positive side. So from my perspective, I'm not a rock physicist, it just generates a gap. When you open a crack, you generate a space. Even for a very short amount of time, that space is generated like a very low pressure environment. That would be decompression that I envision. And that could justify what I've seen, mainly petrologically from a PT diagram. So that's a decompression I'm speaking about. No, only that, where you generate a crack. It's not the entire rock decompressing. Yeah. It is to satisfy geochemically what I've seen and been analyzing carefully, the pseudotachylite. Of course, there is here, I did all this, I've been flying probably too fast when I explained that. Of course, there are, you see, a lot of calculations about how much fast is water diffusion, what is the thermal diffusivity parameter for this type of rock composition. But again, there are also some assumptions. So also, that's why I call the pseudotachylite produced in this way sort of near equilibrium conditions if all these parameters are satisfied. For instance, pseudotachylite, this one is beautiful, very small. Therefore, I don't have a lot of, it's not a chunk, a very fat, thick pseudotachylite, where you have a much larger length of thermal and water or chemical diffusion. Therefore, it would be problematic now to model that. Second, this is a pseudotachylite that has not been reactivated. There are also pseudotachylite that have been used multiple times. That is impossible to model. I don't know how many times it's been reactivated. This one, also based on the geochemical analysis, looks like it's a single event. It has not been reactivated again in the same host rock. Yeah. Oh, so also, yeah, because Jenny, when you have pseudotachylite, say you may generate also sideways hypoxia or dikelets or veins, or you have a mass loss. Now, this one, of course, I capture the best view in the field that then on site have been able to take as a sample and recutting for the analysis in the lab. Essentially, this was just a single layer for the entire extension of the outcrop, and that was about 1 meter long outcrop with no other evidences that maybe this material was coming from elsewhere. Plus is glassy. That's all. Compared to the dikes that are also present in this Balmuccia periodite, it's not a plutonic rock. It's really glassy. So that's another evidence is a pseudotachylite. Thank you.